Swayam Prabha. Digital India. Educated India.
Okay, so in this lecture, I'll be solving some problems, numerical problems. There are three problems I will be solving. First would be on calculating the tower diameter from pressure drop calculation, and then two other problems related to operating line, minimum liquid flow rate, and then driving force calculations. Okay, so let's deal with this first question here. So it goes like this. So the sulfur dioxide is to be removed from a gas. So SO2 is the solute, and the gas has a characteristic of air. Okay, so the chemical details of the solvent and the gas is mentioned here, and by scrubbing with an aqueous ammonia salt solution in a packed tower which has about 25 mm ceramic interlac saddle. So packing material is mentioned. The gas entering at a particular volumetric flow rate, it is also given in terms of English units, feet cube per minute, and the corresponding temperature, pressure, and the composition of sulfur dioxide is also mentioned in the gas phase, and this needs to be nearly completely removed. Okay, basically we are looking for like pure gas. Okay, all the SO2 should be removed in the outgoing gas. The washing solution is entering at a particular mass flow rate of 3.8 kg per second, also given in terms of pound per minute, and its density is given in both units, and viscosity also is given in both units, and we need to calculate the tower diameter. In this problem, explicitly the pressure drop was not mentioned, so we say that we use 1 inch of H2O per feet because this is something close to the flooding limit. Okay, we will take this as a maximum pressure drop that is allowed. Okay, so this would mean the corresponding diameter would be something the minimum diameter that is possible. Okay, anything you want to have higher than the diameter. So like before, we would like to sketch the details in a diagram. So we have a packet bed. So gas entering in, so this is G1, GS, Y1 and capital Y1. It did not mention that the flow is counter current, but we will assume this is a counter current because that's a very common operation. And this is packed with 25 mm ceramic interlax packing. Okay, so now let us look at the data. So the gas flow rate is given in terms of volumetric flow rate, and the temperature pressure is also given. So temperature is 30 degrees Celsius, pressure is 1 bar, and it contains 7% of SO2. Okay, so this is 0.07, and then we want the outlet stream to have 0 SO2. Washing liquid enters at a flow rate of 3.8, and it has a density rho L is 1235 kg per meter cube, and then it has a viscosity of 2.5 into 10 power minus 3 kg per meter second, and delta P we would like to use 1 inch H2O per foot of packing. Okay, so these are all the information that we have got from this problem. So the strategy that we will use in this problem is, first we will use this pressure drop curves, okay, which is plotted as a capacity factor versus the ratios of the flow rates. Okay, so I'm talking about the plots of this sort. So what we would like to do is, we will find out what is this value for this particular problem statement, and then we will choose this particular pressure drop line, and then from there we will read the value of capacity factor. From the definition of capacity factor, we will find the gas mass flux, which is gas flow rate divided by the area. From there we will get the area, from there we will get the diameter. Okay, so that's how we are going to do this problem. Now in this problem, we first calculate the factor L double prime over G double prime square root of rho G by rho L. Okay, this is the factor that we need to find out first. And since this is so L double prime and G double prime, these are all gas and liquid and gas mass velocities or mass fluxes, that is mass flow rate by the area. But since I am taking the ratio of the two, the area will get cancelled, so I can very well write in terms of the mass flow rates itself. Okay, so in this particular term, L is known, L is mentioned, rho L is also mentioned, rho G is not mentioned, and G is not directly mentioned. Okay, so G is given in terms of volumetric flow rate. Okay, so G should be the volumetric flow rate, so I will write this as something like Q, okay, volumetric flow rate times the density of the gas. So this will be the volumetric flow rate. This Q is given as 0.8 meter cube per second. Actually this should be per second. Rho G is something we need in this term as well as in this term. So rho G is something we have to calculate. To calculate rho G, the temperature pressure of the inlet gas is given. So we can use ideal gas law and then get the density. Okay, and the density is a mass density, kilogram per meter cube, pound per feet cube. Okay, so using ideal gas law, rho G can be calculated as P by RT times the molecular weight. So this molecular weight, we have to take an average value because this gas is not a pure air, it has both sulfur dioxide as well as air, so we will have to use a average molecular weight. Okay, so pressure is mentioned here as 1 bar. I am going to do everything with respect to SI units and then later on change to English units. Okay, 1 bar is so much pascals, gas constant, and then temperature is 30 degrees Celsius, but we have to use it in Kelvin, so it will be 303 Kelvin. And what about the average molecular weight? So to calculate the average molecular weight, so let me use here, molecular weight average is something like it has got about 97% of air, right? And so I will use the air molecular weight, which is 29, and then it has got, sorry, 93, right? Okay, yeah, this is 93. So 93% of air times the molecular weight of air plus 7% of SO2 with its molecular weight 64. Okay, so this will give me something like 31.45 grams per mole. and I'm going to substitute that here. So the units of this entire P by RT would be moles per meter cube, and we are multiplying this by molecular weight, which is gram per mole. So the net unit of this product will be grams per meter cube, but if you want to do this in terms of kilogram per meter cube, I have to have 10 power minus 3 added here. Okay. So when you do all this, you can find that rho g will be, I have done the calculation here, but you can check this out. This will be 1.248 kg per meter cube, and I can convert this kg per meter cube to units in terms of feet, pound by feet cube, and this will be 0.078 pound per feet cube. Okay, so now I can go back and then calculate the mass flow rate of gas, which is volumetric flow rate, which is 0.8 meter cube per second multiplied by I need to actually convert this also into English units. So G, so Q is 0.8 meter cube per second. I think it's also mentioned in terms of feet cube, I think. Yeah, it's 1690. But this is given in terms of per minute. Okay, so I'll divide this by 60 so that I can make this as feet cube per second. Okay, so then G would be 1960 over 60 multiplied by 0.078, and the units of this would be feet cube per second times LB by feet cube. So you basically get LB per second. That's the mass flow rate in English units, and you will get 2.197 LB per second, which means to calculate this factor L by G square root of rho G by rho L, now I know all the parameters. Rho G is known, G is also known, L is also known. So L is 502 LB per minute, I am converting that into per second because G is given in terms of per second. And rho G is 0.078. Rho L is mentioned in the problem as 77 LB per feet cube. Okay, so if you substitute all this, you should get about 0.12. So that means I have to locate this 0.12 somewhere here, and then I have to reach this curve, and then I have to read this point. Okay, so I mentioned something about logarithmic interpolation. So 0.12 will lie between 0.1 and 0.5. You can use this logarithmic interpolation and then locate that point here 0.12, and then draw a vertical line, and then go to this curve corresponding to 1 delta pressure P pressure drop of 1 inch per feet cube curve, and then from there read the value of capacity factor. Okay, so if you do that, you will see this capacity factor corresponding to the x-axis value of 0.12. You will get something like 1.5. Okay, from the curve corresponding to delta P of 1 inch H2O over 1 feet. Okay, yeah, sorry, I was only telling you roughly, So what you need to do, like the problem I did in one of the previous classes, you take a linear scale between 0.1 to 0.5, find the location of 0.12, okay, and that if you do, you will come close to 1.5 if you do it in a pen and paper, okay. So now all we need to do is we have to use this definition of capacity factor, okay. So capacity factor Cp is G double prime F over 0.5, kinematic viscosity power 0.05, square root of rho g into rho L minus rho g, okay. This is the definition of capacity factor. So in this problem, we know the capacity factor, we want to find this gas mass velocity. This parameter F should be obtained from the packing data, okay. So if you go to this data I showed in one of the previous classes, so you take this particular packing data. So packing is given in terms of inch. So 25 mm is close to 1 inch. So I can take 1 inch data, and then I look at the interlac Sodals ceramic. So I should be getting something like 92. Okay, 92 is the packing parameter. F is 92 feet inverse. And then we need to know what is the kinematic viscosity, and the kinematic viscosity is for the liquid. So you will have to do the viscosity of the liquid divided by the density of the liquid. I think both data are mentioned here. So you can see the viscosity is mentioned as well as the density is also mentioned, okay. So this is (2.5) into 10 power minus 3, I think, yeah, 10 power minus 3 divided by 1235. So this will be in meter square per second. This will come out to be 2.024 into 10 power minus 6 meter square per second. 10 power minus 6 meter per second is actually 1 centistoke. So it's 2.024 centistokes, and this is the unit that we want in this expression also. Well, I think we know everything here, so we can solve for G double prime, which is nothing but G over area A, and this becomes capacity factor okay. So now you can substitute all these numbers that we know here already. So capacity factor is 1.5, rho g is 0.078, rho L is 77, F is 92, and kinematic viscosity is 2.024 power 0.05. And then from here you can solve, and G also is known, G is also known, and we can substitute that, and then you can get area. So if you solve this, you will get area to be something like 5.94, and this will be the units of feet squared, okay. And from here you have to calculate the diameter as 4 times area by pi square root, okay, and you will get something like 2.75 foot. This is the answer. Some of the other, so this is the third problem. The first two problems you must have solved in the previous tutorial class. How many of you did first two problems? Only one was given? No, the question paper was uploaded in Moodle. You didn't look at the Moodle. Moodle has about 5 questions, I think, right? 3 or 5. Yeah. No, there should be 5 questions because I added 2 more questions. So there should be 5. Initially, I uploaded 3 questions, and so practice. I mean, the purpose of putting this question paper in the Moodle is that you have to work it out. We are only doing some model questions here. Okay, we won't be able to solve all the problems here. So it is on you to kind of test some of those problems. Okay, so we will move on and then do another problem. So this is the first question in tutorial 3. So tutorial 3 problem sheet is uploaded in Moodle. It's kind of fairly an easy question because in the previous class I did a little bit more involved question of this kind. This is straightforward, and you can do this analytically, okay, without any graphical resort. So what's the problem statement? The problem statement is that a gas stream, it contains 95 mole % of CO2 and 5 mole % of ethanol. Here is a small spin. Generally, we try to remove CO2 from a gas, but here CO2 is the solvent and it has 5% of ethanol. So we want to remove ethanol from the background CO2. Okay, so this problem is kind of trying to confuse you. Which one is actually solute? Is it CO2 or ethanol? Okay, so here CO2 is more like an inert gas and ethanol is something that we want to scrub. So a gas stream containing 90% CO2 and 5% ethanol is to be scrubbed with pure water, because solubility of course CO2 is also soluble in water, but ethanol is far more soluble than CO2. So we have to assume CO2 is not really soluble in this problem. Generally in other problems we assume CO2 is actually soluble in water or aqueous ammonia solution and etc., etc. But in this problem the solute is ethanol and the liquid is water, and we are assuming only ethanol is transferring from gas phase to liquid phase. And here the counter current is explicitly mentioned. If it is not explicitly mentioned which operation it is, you are going to use counter current. If it is co-current, it will be mentioned. So we are talking about absorption column, and here they clearly say we want to remove ethanol. Okay, already it tells you what is the solute, no confusion about this. And the desired composition of ethanol in the exit gas stream is 0.5 mole %. So exit concentration of ethanol is given, inlet is also given. The equilibrium mole fraction of ethanol in the gas phase is related to the liquid phase as a equation. So something like a Henry's law sort, okay, linear equation. Here you can see assume CO2 is insoluble in water. This is a very specific assumption for this problem only, okay, because we have a more soluble gas like ethanol in this case. And then we are going to neglect evaporation of water, okay, but water also will evaporate. But we want to keep it as a one solute transfer problem. We don't want to deal with multiple components. We don't want to have water entering into gas and CO2 absorbing into water. So then you will have, like, if you allow that, what you would have in the gas phase, you will have CO2, ethanol and water. In the liquid phase, you will have water, ethanol and CO2. So 3 component mixture in both phases. You can handle it, but may not be in a analytical form or in a pen and paper format. You have to do a little bit more numerical ways. But as far as this course is concerned, like I said in the beginning, this is going to be only one component transfer. Okay, multi-component we won't be discussing here. All right, and then what is mentioned here is the water flow rate is twice the minimum. Find the mole fraction of ethanol in the spent water. Okay, so this means we have to first find what is the minimum water flow rate and then take twice of that. For that flow rate of water, what would be the exit composition for the water phase? That's what we want to find out. Again, we will do a simple diagramic representation of this problem. So gas in, gas out, liquid in and liquid out. You can see that this problem does not mention anything about the packing or nature of the packing column, everything, nothing it says about it, because this is not to do with pressure drop calculation or diameter calculation. This is only a mass balance, material balance. Okay, so we have to assume it must be some mass transfer operating equipment. It can be a packet column, it could be other weighted wall column or some other kind. which we don't have to pay attention to this particular problem. Whereas in the previous problem, you might have seen a lot of details about the packing material, what is it made up of, what should be the pressure drop, all the details was given, because there we wanted to find out the diameter which involves pressure drop. Here pressure drop calculation is not important. Focus here is to look at the material balance, what should be the minimum flow rate, and then if I have an actual flow rate which is twice the minimum, what will be the exit composition, which is purely a material balance problem. No pressure drop, no mass transfer, it's just purely a material balance problem. Okay, so let's see what are the things we know. So here the gas has about Y1 of 0.05. Okay, that's 5% of ethanol. And let me also say a solute here is ethanol. So X and Y, these are all compositions of ethanol. And then the desired composition of ethanol in the exit gas, that is Y2, is 0.5 mole %. So that means 0.005. And the equilibrium line is also given. Okay. So the approach that we can do is maybe first I'll show graphically what we're going to do, and then we'll do analytically. So imagine that you have the Y versus X diagram, okay, and we have got the equilibrium line. The equilibrium line is given in terms of mole fraction, but here I am plotting everything in terms of mole ratio. That's why I didn't say it is a straight line, but it is a function of the mole fractions. But actually it is straight line up to certain concentration. After that it will take a slightly curved nature. Okay, for now let us say this has a particular form, and we want to locate the operating line here. So what is given is the water pure? Yes, pure water. Okay, so that means I also know X2 is 0. Okay, as far as absorption column is concerned, this X2 Y2 you can mark it somewhere here. This is 0.005 and X2 is 0. Okay, so we want to, this is the one point that we have to meet. The inlet concentration is 0.05. This is Y1. Actually this should be capital Y1. Okay, so Y1 will be 0.05 by 1 plus 0.05. It will be so let me calculate this. This capital Y1 will be 0.0552, I think. Yeah. From small y1, I am calculating the capital Y1, and that should be somewhere here. Okay. So similarly, this small y1, small y2 and capital Y2, they are almost the same because it's 0.005. So if you calculate this, I think you'll get something close to this. So we can keep it 0.005. So then this is a line. Okay. So generally, when we look at the minimum liquid flow rate, we assume that the equilibrium line will be curved, and then the operating line should be the one that has the slope barely touching the operating line, if it's a curved line. But here I said that this equilibrium line is almost linear, and your operating line is also linear. We know that in the units of mass mole ratios. So what we want to find out is, you have to draw a line from here to here. Okay, this is a straight line, so that this is a touching point. Corresponding to y1, the operating line should touch the equilibrium line, so that the outgoing liquid will be at equilibrium with the incoming gas. Okay, and this will tell us what is the equilibrium composition corresponding to the minimum liquid flow rate. But we don't want that. We want to have a liquid flow rate which will be twice. So what you will do is, you have to find the slope of this. From here you will get the minimum gas flow rate, and then multiply twice. So you'll get another line, operating line, that will come somewhere here, which will have a slope twice of this slope. Then you, from here you read what is the value of x, and this is the answer that we are seeking. So first we draw the equilibrium line, and then we identify the operating line. The one point of the operating line is fixed. The other end of the operating line is flexible based on the desired liquid flow rate. Now the minimum liquid flow rate is the one where the operating line touches the equilibrium line. Okay, from here I can get the slope, and that slope will give me the minimum liquid flow rate. From this I multiply 2, so the operating line slope will become twice of this. So you can identify that to be somewhere here, and then see where this line touches this y1, and then the corresponding x1 is what we are going to do. So if you want to do this graphically, this is how you will do, but this problem can be analytically also solved. Okay, but the principle is the same. The first thing you have to do is you convert this mole fraction based equilibrium line into a mole ratio based equilibrium line. Okay, so then you will get this. If you do this, you will get this as the equilibrium line. Okay, so this is in mole fraction units, and this is in mole ratio units. However, if you look at this, if you plot this in an Excel sheet, you will find that if y is less than 0.06, this is almost linear. So that means as long as I have a composition y smaller than 0.06, I can simply write this as just 2x. Why I am saying 0.06? Because the highest value itself is only 0.05. The composition I am not going beyond 5%. Okay, for this particular problem, up to 5% or up to 6%, the equilibrium line is a straight line, whether you use mole fraction or mole ratio. So I can simply write this mole fraction into mole ratio. Okay, but the actual expression is this. Okay, if I go to larger concentration, something like 15%, 20%, then you have to use this full equation. This linearity will not follow. The curve will actually, this line will actually curve like this. For this problem, since the composition is only 5%, up to 5%, this is linear. So we can go ahead with simply writing y star is equal to 2x. So that is one simplification. So now we can do a mass balance. So this is the mass balance. So what this equation tells you is that if you have fixed y2 and x2, like here we have fixed it, y1 is also decided, which is here, the value of x1 will depend on the values of ls and gs. Okay, so there are only two unknowns here. If you fix one of them, the other one can be found. Either you can fix x1 and find the ls gs, the ratios, or you fix the ratios of ls gs and then find what the l1 is. So like I said, initially we want to look at the minimum liquid flow rate. I know that this has to be a point, the x1 has to be at equilibrium with y1. Okay, so if I write this for minimum flow rate, this x1 will be just x1 star and if you want to know what is x1 star, what is x1 star? No, not 2 times, it's half, right? From here will be y1 star, y1 by 2. Okay, so what is y1? y1 is 0.052 and divided by 2, so this will be 0.0256. Okay, So what we have done here is, we have identified this x1 star as an equilibrium with the y1 value. So that was exactly this point. Okay. So now we know this equilibrium value of x1 star, and from here I can find out what is the LS by GS minimum, and this will be nothing but y1 minus y2 divided by x1 star minus x2. So y1 is 0.052, y2 is 0.005, x1 star is 0.0256, and x2 is 0. So from here you can find the minimum gas flow rate, liquid to gas flow rate is 1.835. Okay, so that is this slope. But the actual flow rate is twice the minimum. So then you have to do this 2 times 1.835, and this becomes 3.67. So that would be the slope of this line. Okay. So now in this problem, we know the slope, we know this point, and we have to find this point. Okay. So we go back to this problem again, the general material balance here, and then you're going to solve for x1. So from this equation, the x1, 3.67 is it? Yeah, 3.67. So from this equation, mass balance equation, you can solve for x1. This will be x2 plus GS by LS into y1 minus y2. So x2 is 0 because the pure water, pure water, and GS by LS will be 1 by 3.67, y1 is 0.052, and y2 is 0.005. Okay, so x1 will be 0.0128, and if you write in terms of mole fraction, this becomes 0.0126 or 1.26%. So the outgoing composition here, X will be 0.0128, or x1 is equal to 0.0126. So this problem kind of illustrates multiple ideas that how to calculate the minimum liquid flow rate, and once you have that, you can operate it with multiples of that minimum flow rate, in this case twice, and then you get a new operating line, and the corresponding to the new operating line, you are going to get the composition of the outgoing liquid. So this problem is analytically solvable only because the equilibrium line is a line. Okay, if it is curved, you have to do it graphically. Okay, but the operating line will be always straight line in this mole ratio units, but in the mole ratio units, equilibrium line may or may not be straight line. That's something you have to look at it. So what I did was I plotted this function in Excel, and I looked at up to what limit it is linear, and I found that up to 6% this equation is linear. Beyond that, it becomes slightly curved. So for this problem, since the maximum composition is 5% only, I assume this to be a straight line. Okay. So what it also means that if the student don't convert it in these units, they will still get the right answer. Okay, so the benefit of that is given to the student. Okay, if I were to set a question paper, I will not do this. I will make sure that you will get a wrong answer if you do this. Okay, but probably this is one of the gate question, or maybe a gate question, so they make sure the student get it right regardless of which approach. Okay, let's go to the third problem. The third problem is also very interesting. I mean, each problem tries to bring some new elements of learning. So this is the last problem in the tutorial sheet uploaded in Moodle. So this problem actually, I mean, we have never seen this kind of problem in textbooks or in gate questions. This is something we came up with. I mean, one of my TAs, they came up with this question. because it also kind of illustrates the driving force calculation that we generally do in heat transfer. In heat transfer, we calculate this log mean temperature difference for the co-current and counter current. In the same way, in one of the classes I mentioned that analogy between heat transfer and mass transfer with regard to the average driving force. For example, in the kind of co-current, there will be a large mass transfer driving force in the beginning, and then this mass driving force will diminish towards the other side. Whereas in the counter current, you can pretty much keep the driving force pretty much uniform across the operating equipment. Okay, so that's why we often go for the counter current, so that the driving force is almost equal, so the mass transfer rate will be equal throughout the mass transfer equipment. So here, this problem also tried to kind of illustrate that principle a little bit more. So what we have here is, we have a ammonia stripping problem. So ammonia is to be removed from water in a co-current stripping operation. Okay, I am bringing two differences. We are talking about stripping operation, not the absorption. So operating line is going to lie below the equilibrium line because it's stripping, and then I'm saying it is a co-current. So far we have done only counter current. Okay, so we have to adopt the co-current operation, and we have to solve this for stripping operation. And here the ammonia is transferred from water to air. Okay, the other way around would be absorption problem, but here we are talking about the opposite problem. Okay, that's what's called stripping operation. And then the inlet concentration of ammonia in water is 10 mole%. Concentration in the outlet is given 3.3 mole%. Air is supplied in some volumetric flow rate. Temperature, pressure is given, and then it contains a dilute amount of, some amount of ammonia is already present in the inlet gas itself. The flow rate of the pure water is 250 kg per second. Assume that the following equilibrium line is y equal to 2x, and what we need to do is calculate the log mean driving force in the liquid phase that exists across the column. Okay, that's what we want to do. So graphically, what we are willing to do is, let's say you have a equilibrium line here, and how will the operating line for a co-current stripping operation be in this plot? Any guesses? Can I just draw like this? It should have a negative slope or positive slope? It should have a negative slope. Yes, it's going to have a negative slope. And can you tell me where the so suppose if I draw the plot here, the packing stripping tower, the flow rate, the flow direction will be the same. Gas will always enter at the bottom, and here liquid is also entering at the bottom, and the liquid is going up, and the gas is also going up. Okay, so we will keep the same nomenclature like before. So this would be y1 g, and this is y2 g2, this is L2 x2, this is L1 and x1. Okay, so where will x1 y1 be in this plot? So x1 y1 corresponds to where should I look at this L1 x1 y1, where would that be? Is it going to be here or is it going to be here? And how do you decide that? So y1 is the smallest, right? And the x1 will be the highest. So where is that? That point should be somewhere here. Okay, so this is basically the bottom corresponding to this point, and this one, the operation moves along this way. So the gas phase composition is increasing, but the liquid phase composition is decreasing. Okay, so that you can identify here as top. So in this problem, we want to find out this particular operating line. Once we do this, what we are asking is calculate the log mean driving force in the liquid phase that exists across the column. Okay, what that means is, once you do this, at the bottom, the average, at the bottom, the driving force for mass transfer is this, the distance between this point from the equilibrium line to this point. That is the driving force for the liquid side mass transfer. If you go to the top of the tower, there the driving force would have been just this. Okay, so this is the driving force at the top and this is the driving force at the bottom. So if you imagine this, you can call this as delta x1 and you can call this as delta x2. Okay, now the log mean LMTD or LMDF, log mean driving force, is basically delta x1 minus delta x2 over ln of delta x1 by delta x2. Okay, this is what we have to find out. So if you look at this problem, all the things are given for you to find what is going to be the x2 y2. Okay, so for example, ammonia is removed from this. The inlet concentration of ammonia in water is 10 mole %. Okay, so this is actually 0.1, and the concentration outlet is 3%, and air flow rate is given. You can actually calculate the, so volumetric flow rate is given, temperature pressure is given. You can use ideal gas law, you know the average molecular weight, you can know what is the density, and then from there you can get what is G1 is, just something similar to what we did in the first problem. Okay, and the flow rate of pure water LS is also given, that is 250 kilogram per kg per second, and the equilibrium line is also given. So all the information that you need are given so that you can easily calculate what is the x1, you can calculate the y2 values. Y1 value is also given, I think it's about 0.01 mole %, right, 0.0001. Y1 is also given. So Y1 is given, X1 is given, X2 is given, Y2 we have to find out. Okay, to find out the Y2, LS, GS also is given. The only unknown was Y2, so that is somewhere here. Okay, once you know the Y2 here, and you corresponding to the Y2, you can calculate what is this X2 star, the equilibrium liquid phase composition. So then you know what is this delta X2. Since Y1 is already know, you know what is this X1 star, and you know what is the delta X1. Okay, from here you have to just use it. Okay, okay, we'll continue from this previous discussion. So first let's convert all the mole ratios, mole fractions into mole ratios, because this comes under a concentrated mixture, as we talked about 10% in the liquid phase and 3% on the outlet of the liquid phase. So we need to work with the mole ratio units. So x1 is 0.1. So from here, if you calculate capital X, this comes out to be 0.11, and similarly Y1 is 0.0001, and if you convert this into capital Y1, this also will be 0.001, and x2 is 0.033. So from here the mole ratio x2 is 0.034. Okay, so you have converted all the mole fractions into mole ratios. The next step is to find out LS and GS, so that we can find out the operating line. So as far as LS is concerned, LS is mentioned in the problem. The flow rate of pure water is 250 kilograms per second. We will convert this into a molar flow rate. So you get 13.89 kilomole per second. Okay, so this is LS, and then to find GS, we need to use the ideal gas law. you can see this temperature pressure of the inlet stream is mentioned, and it contains very little amount of ammonia. So we can actually practically we can consider this inlet gas to be almost pure air, because it is 99% pure. So GS is basically referred to the mass flow rate of air. So we calculate this by P by RT into volumetric flow rate. So pressure is 2 atmosphere, so or we say 2 bar, and the volumetric flow rate is 600 meter cube per second, and temperature is 30 degrees, so 303 Kelvin. Okay, so the units of this would be so the units of this expression would be moles per meter cube times meter cube per second. So basically moles per second. So if you solve this, you will get GS is something like 48.2 kilomole per second. So you will get an answer in terms of mole per second, but you can convert that into kilomole per second. So we know LS and we know GS now, and then we can use the operating line or the mass balance. So this is written for co-current flow. So from here we can solve for Y2. So Y1 is 0.0001, and then LS by GS. LS is 13.89, GS is 48.2. Both are in the units of kilomole per second, so they cancel out. And X1 is 0.11, and X2 is 0.034. So from here we can solve for Y2 as 0.022. Okay, so that means in this particular graph, so we have identified what is Y2. So Y2 is known, and then corresponding to Y2 we can find what is this X2 star from the equilibrium line. X2 star is in equilibrium with Y2. So we use the equilibrium line, which is nothing but this is the equilibrium line equation. So we substitute Y2 here and then calculate the X2 star from here. So if you do that, you will get X2 star as 0.011. So going back to this particular graph, so we have found what is the value of X2 star. So now the driving force at the inlet delta X1 is X1 star minus X1, and similarly the driving force at the outlet or at the exit is delta X2 equal to X2 star minus X2. So this X1 star is in equilibrium with y1. So you can calculate that x1 star from the equilibrium line, and you will get x1 star as 5 into 10 power minus 5. So from here you can calculate delta x1, which is nothing but so driving force at the inlet is delta x1, and that is x1 minus x1 star, and similarly the driving force at the outlet is delta x2, which is x2 minus x2 star. So here x1 star is the concentration, is the mole fraction which is in equilibrium with x1 star is in equilibrium with y1, and similarly x2 star is in equilibrium with y2. Okay, so both x1 star and x2 star, x1 star and x2 star you can calculate from the equilibrium line for this problem. Okay, so that means you can calculate for x1 star like this, and similarly for the x2 star you do like this. So from here you can get x1 star is equal to 5 into 10 power minus 5, and x2 star comes out to be 0.011. So we use these equilibrium values and get the value of delta x1, which is 0.11 minus 5 into 10 power minus 5, and delta x2 is equal to x2 is 0.034. 0.034 minus x2 star is 0.011. So from here we calculate the log mean driving force difference is delta x1 minus delta x2 over ln of delta x1 by delta x2, and this comes out to be 0.055. Okay, so the log mean driving force existing in this particular co-current operation is 0.055 in terms of difference in the mole ratios.